Oh god, my head hurts. So, I have an idea for doing a tile map using ray marching. But the thing is, that could get complicated very quickly. So to keep the first prototype for this kind of simple, we're just going to use an orthographic camera, which is going to simplify what geometry we need to look for intersections. And by using an orthographic camera and having that orthographic camera looking straight down on our tile map, we can easily partition the space and know which SDF objects we need to check for collisions. So for this first prototype, I'm really tired. So we're going to try to just make a tile map that's like hard-coded into the shader, and the tile map will just be either a sphere, maybe a box, and then nothing. So depending on the tile value, we'll display a different SDF object inside that tile, and that'll be a good first go at this. We'd want to eventually add something a little bit more complicated, something where the SDFs are kind of like merged together on a tile by tile basis. We could like mix some auto tiling in there. So I guess yeah, we'll just give this a shot. And see what happens, I guess. I'm gonna wait till the timer hits 0 before I start. So, if you're just getting here, if you're just getting here, doesn't, that's fine. There's one viewer, I believe that is myself, pretty sure. We can make sure. Since we got the little chat thing open, might as well. Okay, now, if I had other viewers, I'd actually maybe direct this towards, I mean, as long as the stream is small, I can direct what I'm doing towards where people want it to go, but I don't anticipate that happening. So I'm going to try to go faster than I did last time, but we're going to try to get all this stuff done on this agenda here. Orthographic camera, remarch setup, lighting calculations, and hard-coded tile map. Now, we might not make it awesome, but we're just setting the foundations, right? We're doing a proof of concept, getting practice on those fundamentals and whatnot. I should probably open the old code and move the editor over here. And we'll take this old header, and we'll take this SDF 005. It's where we're at now. We'll just get these 5s. And that paste bin URL, I don't know what the paste bin URL is, but we got the tiny URL up here. And the paste bin URL, I can check that really quick. And I don't have a graph today. Okay. And we can all right. Let's get at it. Okay, let me make sure that everything is situated where it needs to be for people to for it to. Okay, does that layout look good? Yeah, that layout looks good. Okay, let's okay, so anyways, let's get to this. We're gonna need to just take the shader code that is over on the top right. You can't actually see that code, so usually I'm not gonna go down here to this code here, because I'm just going to use the window over here for the code, and then I'm going to just paste it into... no audio, really? Okay, huh. I guess I'm gonna have to check Twitch really quick, make sure there's actually sound, because I'm being told I don't have sound. So let's, that would be bad to not have sound. So let's go to Twitch. Yeah, that's what I thought. That's what I thought, that we actually did have sound. Well, the sound used to be called Samsung Won't Persist, but, you know, I thought that when I decided to rename the microphone, that Samsung Won't Persist was a little bit obtuse of a name, so I just wanted to be much more concise and technical. Therefore, I chose the very descriptive technical jargon of Soundboy, which, you know, Soundboy is a thing, I think, or maybe that's Pool Boy. I don't know. Doesn't matter. Okay, so anyways, let's continue. So this code right over here in the shader toy window, it's right down here. This is my my right monitor. I'm only gonna be really looking at, I'm probably gonna keep just the shader in the view and not this actual code, because the code is gonna be over on this side, and I'm gonna change it here in my editor of choice, and then I'm gonna paste it directly into the monitor over here when I'm ready to reload it. Just because we want to optimize the usage of our space, and we're going to optimize the usage. We're going to just optimize our space. anyways, let's do this. So we're gonna take this and we're gonna paste. And the first thing is we're gonna get rid of some of these comments, just because we don't need them. I am pro verbose comments, but I've done this part so many times that I just don't wanna deal with it. So we're gonna do frag chord minus 0.5 times I resolution dot xy, and then we're going to divide by, I believe, yy, and that's going to get us our frag coordinates centered in the screen. And then for the color, rather than doing all of this bullshit, we're just going to take the length of the UV vector. And actually, I'm going to take the length of UV like that, and I'm going to rename UV to U_V, just because I like to keep things as 3 or 7 letter variable names, because I'm kind of OCD like that. We're going to take that code, we're going to paste it, and see what I screwed up, because I always screw up something, even though you think that would be very trivial. Dimension mismatch, we got a dimension mismatch, float, and vector. So if I look at this code, yeah, no, that can't, yeah, okay. How is color? Yeah, that makes sense. So we want to do a vec3 here, because the length, actually the length is, we'll rename that to length. So this is just a float value, because the length of a vector is a scalar. And then we'll do vec3 color over here equals a vec3, where we take a actually no, is a vec4, sorry, where we take the vec3 of length, so we just duplicate length 3 times to get it into the x, y, and z slots of a triplet, and then we do 1.0 for our alpha value, and then we have a nice little color vector, and we will take this and we'll just put color. And now, I don't know, should color be a vec4? I don't know, but it is now. So let's take that and let's paste that into Shader Toy, see if I screwed up anything. And we'll just keep on going until I haven't screwed up anything. Dimension mismatch. So once again, I said that this was a scalar now, and I forgot to rename it to float. And okay, so now, maybe if we're lucky, I haven't screwed up anything. So take that and run that. Okay, so now we actually have something, so that's cool. It seems that there's some things going on in the chat, and it looks like they did not actually check out my extensive resources. So hopefully they can go there. There's also some other resources you can look at in the chat. I have a large, extensive list of anatomical knowledge hosted on the internet for free. Most states will require that you're at least 18 to, have that stuff. But it's good information to have. So, I see that there's some flaming going on in the chat, but I'd like to keep this as professional as possible. Okay, so anyway, so this gradient here is just a good visual indicator that we have our transformation of those fragment coordinates correct, right? Because the black is in the center, 0, 0, and then, right, it fades out on the x, it fades out on the y as well. So let's set up a orthographic camera. So actually I said I wasn't going to do the editor there. So over here, we want to keep this part, and then these things we may change later. So we want a we basically want a... This camera is going to be simpler than other cameras just because the geometry isn't going to distort depending on how far away the camera is, because we're just going to use some rays that go straight down. So what we can do is we can just say vec3, and we'll just say ray, and this is the camera ray, and this is for the orthographic camera, and we'll just say vec3, and it's uv.x, uv.y, and then for the direction, it's just pointing straight down, and straight down is going to be 0, -1, because our camera is above the scene, and we're using like a Z-up model. Because I think Z-up just makes the most sense, right? You keep XY like they usually are when you're in math class, and then you just stick on a extra axis that comes, you know, up off the paper, right? And so as the things on your graph paper are coming towards your face, that is increase in the Z, and as you go into the paper, you are decreasing the Z value. So yeah, we'll use this for the ray. So this is orthographic camera ray. Okay, and now we need to actually somehow render that ray. So we'll say vec for color equals SDF render, and we'll use the ray. And then we can just get rid of this stuff here, and we'll create a SDF render function that returns a... Do we really want a vec4? No, we don't really want a vec4. It would make more sense for the... You know, but for the sake of keeping our data normalized, let's just keep it a vec4 SDF render, and then a vec3, which is going to be the ray. Okay. And for now, we'll just return the ray.x, ray.y, and we'll return 1.0 for the xy. Well, no, we'll just return, why not? We'll return the z, and then we'll just 1.0 like that. So this is not the actual calculation, this is just us stubbing this in to see what it's going to look like. So from there, we're just expecting to get kind of like a color gradient now. So back to the original color gradient. So let's give that a shot and just see what we screwed up, because I always screw something up. So, you know, failure is a prerequisite to success. So, you know, that's the way I think of it. So, so I obviously made a mistake, which, you know, you gotta actually say it's a vec4 when you're returning it. You can't just return a series of parameters. Return is not really a function. I just have a habit of doing it like it is a function, just because in JavaScript they inject semicolons where they don't belong a lot of the time, and writing it that way kind of like helps avoid weird things that are impossible to debug. Okay, so now this looks good to me. Now, we got this big black blob here, and that's because we centered our fragment coordinates, right? They're adjusted so that 0, 0 is in the center. If we want a little bit of confirmation that, you know, this is actually the center here, we could probably just do like a absolute value of the array x and array y. So we could do like abs array x and then abs array y like that. And if we take that and we paste it in there, we should have, okay, there we go. So that makes sense. That looks right. let's just take where we are, and I'm going to put that on the paste bin. So I'm just going to edit the paste bin URL really quick and put the current snapshot of where we are with the code. And save changes. Okay, so that's you can go to tinyurl.com/SDF-005 to get to that. Okay, so I'm gonna keep going. So a lot of times debugging can be very difficult in a shader, and so we will kind of paint colors to kind of do sanity checks to be like, are we really working with the value sets that we think we're working with, right? Like we have a color gradient right here, but the color gradient, all that really is it's just a data set, right? Like everything in a computer is just numbers. Like anything you see, it's just numbers. So with that, I'd say that looks correct. So let's figure out how to just render a single piece of geometry. So we're gonna do a float, and it's going to be, well, hold on, let me think. Yeah, there's some other things I would like to do later, maybe another stream, but let's keep this as simple as possible. And so this is going to be SDF all geom. Actually, no, it's not, because we are going to use like a Tilemap structure. So we're just going to do SDF sphere, and we're going to use a vec3, and it's going to be point on path. And yeah, that's all we need. So we just want the sign distance function of a point on path in relationship to a sphere. So how close is this point on path to a sphere? Now, when we give this point on path to the function, we don't actually, this function is not aware of the path that it's on, right? Because this is a point that is part of like array in point normal form. But we're just extracting the point off of it in space and discarding the other aspects of it, because all we care about is the point on path and its XYZ value. We don't actually care about its trajectory. We just care about where it is, so that we can figure out how close that point is to the sphere and return that number. If we are inside the sphere, it's going to return a negative number. So let's just hard code a sphere at the origin. So we'll say vec for object equals vec4. It'll do 0, 0, 0 is the origin, and then way over here we'll put a radius of should we just keep it as 1? That would probably be the easiest way to do it. Yeah, let's just keep it at 1. Now, if we want to actually make a tile map, this is going to mean that this one tile that contains the sphere is going to be very large. So we might have to figure out how to zoom in and out with the orthographic camera later. Okay, so then the float dist, or let's just do dis for distance, equals the length of the object dot xyz minus the point on path. We could just do point on path because it already has xyz, but let's just do xyz like that to be explicit. And then all minus the radius of the sphere. So obj dot w. W is the last element right? Because after Z, you kind of run out of numbers, so they just do W. So X, Y, Z, W, and W is our radius. And we can make a note of it right here. Okay, so now that we have that, let's just return the distance. And we're not actually going to expect any results yet. But what we do want to do is just make sure that that's still running, that we don't have any like syntax problems. So giving that a shot, actually no syntax errors, which is a surprise because I usually mess something up. So with this SDF render, let's get rid of this and actually put in ray marching algorithm. So we're going to say that vec3 point on path equals oh, interesting. So since it's orthographic, so what we're going to do is we're going to have a, even though it's orthographic, and so this is redundant, we're going to have a camera origin and the ray, just because, you know, eventually we might want to not have the camera orthographic once we're robust enough to support that. And then over here, we're just going to say so the origin is vec3 orig, for the camera origin is a vec3, and it's the same thing. The ray comes out of the actual grid on the, I've been calling it like a phosphoric grid, or like a CRT monitor grid is what I've been calling it for our model. But to get it orthographic, we need to make sure that the ray that we're drawing from the camera lens to the surface we're striking to create our image, we want those rays to actually strike that surface perpendicularly. So we don't want any angled rays. So to get that to work correctly, we just need to make sure that these X and Y points just line up correctly. And then for the origin, this Z value for the origin really doesn't matter because the camera's orthographic, so how far away it is from that screen won't really matter. But we could kind of like at least try to use a value that kind of makes sense. So I'm going to say 0 plus 9, so the camera is like 9 units above the world. But this number won't actually affect anything. And this ray right here is not normalized, so we should really normalize this. So we don't need to normalize the origin. Origin is fine. That's actually where it needs to be. You know, if I was doing something that wasn't shader code, maybe I would normalize it here, and then I would also normalize it in here, like right when the parameter gets in, I would also normalize it. But that's 2 operations instead of 1, and so we need to be a little bit more careful, because being wasteful with memory and processing is not a good idea in a shader. So I'm a little bit more, you know, they have that saying, premature optimization or whatever. I don't know, in a shader, you know, you might want to think a little bit about the cost of your operations a little bit more than you would in something where it doesn't matter if it runs, if it takes, you know, 1 second to run or a half a second to run, it doesn't really make a difference to you. Like when it's something like some JavaScript alert box or something that needs to pop up, or some little calculation that needs to calculate before something is displayed on screen in a UI. Like that stuff, yeah, the difference between a second and a half second really doesn't matter that much. as long as it feels responsive to the user. But here, if something needs to go every single frame, you better be aware of how long things are taking and how expensive your operations are. So with that, I'd say we have the ray, we have the origin. Now this is a very stripped down camera model, even for ray marching, because we don't need as much information when we are doing a orthographic camera. But these two parameters, the origin and the ray, this is enough information for a better camera setup later. You would just do a little bit more calculation over in this area to derive these values. But these values are all the parameters you're going to need for the SDF render, even if you do a more complicated camera setup. So now that we have that, let's calculate the, let's say, point on path, and we're going to call this is going to be distance from origin, and these also need to be floats. So we have a distance from origin, but then we also have a distance from the surface that we're trying to get to. And at the very beginning, the distance from the origin is definitely 0. The distance from the surface is really unknown at this point, so we can't really calculate it yet. We're going to do for int I equals 0, I is less than or equal to max steps, and I plus plus. And then within here, we're going to do point normal form to get the point on path. The point on path equals the origin multiplied by the distance from the origin, right? And then we need a direction, which is our ray. And so this is point normal form. So a ray has a position and a direction, and this is not just the direction, but it's also like the magnitude, like how far in that direction do we go. So the direction, so here's the direction and here's how far we go. So I don't know, maybe you want to write it this way. Maybe that order makes sense, because then you say the origin going, and that's just not a multiplication symbol, the origin, and then going in this direction for this amount of distance to get the current point on path. We start off at 0, so the point on path is coincidental with the origin. So with that, the next step is to actually call the SDF sphere function. So we'll call SDF sphere with the point on the path, and that's going to give us the distance from the surface. Okay, and so now the distance from the origin, and the distance from the surface are these values right here and right here. They are in agreement with each other. They are not off by 1. I don't know why it took me so long on the last stream to like figure that out. But yeah, they are in agreement with each other. I think it's because of the different variables I use. Like, depending on how you name your variables, it'll change how you think about things. And I've written this code, right? This is the 5th time I've done this, so I can definitely vouch for that. So if the distance from the surface is less than or equal to, and we'll do min dst Now we'll do dis for distance like that. So I try to use the first 3 letters of the word when I'm abbreviating, rather than right, because the rules can get really complicated if you don't use the first 3 letters. So I just try to keep it as simple as possible by, when I'm abbreviating, just use the first 3 letters. Now the reason I don't do it for step is just because, STE, that's kind of, well, you know what, to be uniform, why don't we do that? Let's just go with that. I've never done that before. Let's use that for step, even though I think that's a harder abbreviation to read. And then if the distance from the origin is greater than or equal to max dist. So what this is saying is, if we've hit the surface, we want to bail out because we're done marching. We found the surface. If we are going off into infinity, like we shot the ray out into the void and it's not going to collide with anything, we also want to bail out. So we need some type of mechanism there to say, we've gone way too far away, let's just not try to render anything. So, and this max step will also kind of prevent us from going out infinitely far. So we got 2 safeguards there. Let's define those defines. Defines are usually in all capitals in most ANSI, not ANSI, ECMA script style languages, like things like C, C++, Java, ActionScript, JavaScript, C#. I think even Python. Python isn't ECMA script style, but even Python's same convention. So the max step, we're going to use 100. The min distance is going to be 0.02. The max distance is going to be 100.0 to make it a float. Now, I've seen sometimes people will do this. I'm not sure if there's any benefit to guarding your numbers with parentheses in a define. Like, I'm not sure, but I've seen that done before. I guess that might prevent. It definitely has some implications for when macros get a little bit tricky. It does have some implications, which I can't think of right now, but it does. And I don't know which one's safer, but I do actually prefer this style just because macros are scary, and I like to contain them as much as I can. But yeah, without using parentheses, without using parentheses, macros can sometimes interact with each other in like really weird ways. So if we're in the bailout condition, we're just gonna break on out of here, and once we've, if we haven't broken out of here, then we need to keep on marching. And the way we keep on marching is we take the distance from the surface and we add that to our distance from the origin, right? So we incrementally march the distance from the surface every iteration. So every iteration, we say, how close are we to the surface? Oh, we're 5 units away from the surface? Okay, march 5 units closer, right? And then, oh, we're 1 unit away from the surface? All right, now march 1 unit towards the surface. And you might be like, well, that's weird. If you're only 5 units away from the surface and you march 5 units towards the surface, then aren't you on the surface? And the answer is, well, yes, if we were doing like a ray collision with the geometry, but we're not doing a ray collision. We're doing a point in space. We're trying to take the point in space's distance to any surface on the geometry. So we're not trying to calculate, when we're calculating this distance to surface, this distance to surface is just the closest surface to the point, but it may not be an intersection on that surface where the ray is actually going to collide with the surface. So it's just Um, I think of it as the perpendicular distance to the object is a way to think of this distance. But we may not be colliding with the object perpendicularly, right? So yes, if this ray were completely perpendicular to the object, where it's going to line up in such a way that it hits the apex of the object, then yes, if we take this distance and we march this distance, we will hit the object. But usually this ray isn't going to collide head on, and so it'll have to travel a little bit larger of a distance. This ray will have to travel a little bit larger of a distance than this distance here. And that's kind of why we kind of iteratively do this. There's better tutorials on ray marching. I just wanted to go through a little bit of an explanation of what we're doing. And maybe that could also be a refresher to you. Okay, so with these, let's update that distance from the origin. So distance origin, we can do a plus equals, or we could do, yeah, let's just do a plus equals, and that's going to take distance origin and increment it by value we give it. So we're just gonna so we're march forward by ds, right? Okay, so with that, I'd say we can color these really quick to use our fast thinking circuits to see if everything kind of like makes sense. Okay, so I'd say that looks good. So now what we want to do is float hit equals the distance to the surface, and 1.0 minus the distance to the surface. So basically, when the distance to the surface, when this is 0, that means we've hit the geometry. But we want to invert that value so that we get a value we can like multiply with other things and get a result we can see, right? So if we hit the surface, we want this value to be 1, and if we don't hit the surface, we want the value to be 0. So we gotta like flip that, invert it. Then the other thing we want to do is there's the possibility that these values could end up out of the range of 0 to 1, most definitely. So we want to cap them. So we're gonna do a min 1.0 and all of this, and that's going to that's a ceiling cap. So we're going to take the minimum value 1.0 or this, whatever is lower, and so that if this is shooting off into infinity, we're going to cap it at 1, then max 0.0, and this is going to do the floor cap is this, right? So the only way that this value will ever be chosen for max is if this goes negative, right? So this is going to keep everything above 0. This is going to keep everything below 1. Okay. So with that, SDF render is going to return a vec4. So right now, we'll just like return a vec4 of the hit value. And we're going to give that a shot, see if we screwed up anything. I'm expecting to see just kind of like the outline of a sphere, unless I screwed something else. Let's just, so I made a syntax error, and it's the most common thing I do, which is forgetting to add the decimal place when I'm declaring a float value. So let's take that. So that wasn't too bad. Usually I make more syntax errors. So we see like a little dot right there. And You know, it looks kind of small. Um, I mean, I'm not like totally sold that it's incorrect. That looks fairly correct to me. But let's keep going. Let's add the lighting calculations. So to get the lighting calculations, we're going to add it into the SDF render. I've seen it done with the where it's outside of this ray marching function. So this is why I'm not calling this ray march. I'm calling it SDF render because one ray march, because we're doing two things. And you might say, well, then why don't we have a function called ray march, and why don't we have a function called calculate lighting? Well, I'd rather inline everything unless we're going to call it in more than one place, just to make the code, minimize the code's surface area, make it less code, and also make the code just easier to follow. So the calc normal, though, is vec3 surface normal equals SDF. It's not calc normal. I usually don't call it calc normal. I call it like I have some shortcuts. I need to, well, that is not good. Okay, so I usually have shortcuts for this kind of stuff, so I know it's like estimate normal, so I'm just going to write down in my notes that SDF calc normal and SDF calc normal so I call it SNorm for estimate normal. Okay, so just making some notes in my shortcuts just so that I can remember this easier for next time. But I know it's SDF, and I call it SNorm for estimate normal. And we're going to take that point on path that collided with the geometry, or at least we think it did, and we'll estimate the surface normal from there. So we'll do a vec3 and SDF SNorm, and we'll take the vec3 point on path, and that's all we need. And we can't do that. So from here, there is a formula, so we'll define. So we have S, E, X, Y, and Z. So these are our defines. We're also going to undefine them at the end. This is just the way I have been remembering how to like create this function to estimate the surface normal. I'm not really good with my math, so I don't understand the reason for why this formula is this formula, but it works, and it's a estimation of, from my understanding, is an estimation of the surface normal based on like, you know, when you're estimating the surface normal of a 2D circle, you can just take 2 points on the circle that are really close to each other, and then you can just draw a line between them and take the perpendicular, and boom, you got a normal. You can do the same thing in 3D, and that's what this does. I don't know exactly how it does it, but let's just write it. So for this, we're going to do SDF So even though this is just SDF sphere, we should really make a float SDF scene. And for now, just return SDF scene is just a wrapper for SDF sphere, because we will need to be a little bit we'll need to expand on that at a later point. So where we see SDF sphere, we're just going to take SDF sphere and replace it with SDF scene. Sorry if that makes things a little bit harder to follow along. Okay, so from here, we can take SDF scene, and that's this, and then E is epsilon, so it's a very small value that is very close to 0. And then X, Y, and Z is just the point on path dot X, dot Y, and dot Z, right? So these are the pieces of information that we're going to need in order to estimate this normal. So we're going to return and normalize vec3, and then 1, 2, 3, and then the meat of the function is going to go in here, and 1 step forward, 2 steps back. So we have like a positive section, a minus, and then a negative section, and then each one of these is like X, Y, and Z. So for that, we can do vec3 and the surface normal function, and then we're going to do X, Y, and Z like this. And you might be asking, well, where's the other stuff? Let's add a, we said that this side was the pluses. And then over here, we're going to take this same logic, and this is going to be our negative section. You'll notice, well, minus 0, that's kind of meaningless, right? And yeah, you'd be right, but I like the uniformity and the explicitness that minusing 0 can offer. Especially, it's going to make this easier to fill out, because now all I have to do is go like this: E, E, and E, and then same thing here: E, E, and E, right? We can go diagonal and bam, easy. Now, obviously this is a little bit cluttered, and it can be kind of hard to visually see the pattern. So because it is visually hard to see the pattern now that we've kind of constructed it, we might want to just remove those plus zeros so that we can kind of more easily see what's going on there, right? By breaking up the space visually, we can kind of get a better idea of what pattern is going on here. And the pattern, remembering what the pattern is going to make it much easier to reconstruct this from memory. Because, like, that is how I'm remembering this. I'm actually remembering the formula visually. I'm remembering the actual structure. And is that, yeah, so that looks like a bot. Anyway, so this formula, I think, should be correct. I've written enough times where I feel like I got this time. So estimate the normal, and we return normalized vec3, where these are the components. We're taking these different deltas. So some weird x delta, some weird y modified delta, and some weird modified z delta, and then packing them into X, Y, and Z respectively. So yeah, I think that is correct. So we'll give that a shot, and then this is the surface normal here. So we should just see if the code runs. We're not going to expect anything, we're not going to expect anything different, but I just want to see where I made my syntax errors, because I know I screwed something up, because I always do. And I see that in SDF scene, and this is why I don't like to use shader toy, because really I just need to know approximately where the error happened, and then I can fix it right away. But like if I'm looking at if I'm actually trying to, this one isn't too bad, but if I'm trying to read these, sometimes it's just a whole bunch of visual noise, and it's like I just want to know approximately where the error happened, and from just where the error happened I can look at the code and usually know what's wrong. And you're like, well, if you can just look at the line of code and immediately know what's wrong, then why did you make the problem? Why do you make the error in the first place? And well, I think the answer is I'm just looking at that line of code more carefully, right? Um, so with that, let's take this and rerun it again, see if we made any more mistakes. And so our constructor has too many arguments, and then no overloaded function, blah, blah, blah. So I do know what's going on here. It is that like I almost got this pattern correctly because I kind of memorized the pattern, but this SDF scene function takes a vec3, so I just have those values kind of like flipped around. But I almost got that from memory, but so okay. So the more you can remember, the more you can build upon, right? Because if you're constantly recomputing everything, you can only get so far. I know this from just being in math class and wanting to like derive proofs of everything because I was always unsure of things, and that really just slows you down and makes it so it takes more time to calculate things. So like, you know, and that goes with this function where, I know it works, I don't know exactly how it works, but at some point you kind of have to let go and say, okay, it works, I don't know how it works. But you can't simultaneously comprehend and understand everything all the time, right? Even if you did a proof of how this worked, when you're using it at a higher level, you don't want to think about how it works, right? You just want to think about it at that higher level of this estimates the surface normal, and you don't want to go down that deep as to how the nitty-gritty details of how it works. Because if we're working at a high level and you want to reevaluate your kind of like tree of logic every time you do something at a high level, you just wouldn't get anywhere. Because think about the processing power of reevaluating an entire knowledge graph, right? So with that, let's see if our code has any more mistakes. Okay, so we're good there. Okay. So with this estimate normal, this is our surface normal. Now we need a light normal, and to actually calculate the light, we're gonna say vec3 LP, and we'll just put it at for now we'll put it at, I don't know, vec3 0, actually 0 minus 1 comma 0 comma not that. We'll put it above the scene. It doesn't really matter. Well, it does kind of matter. We'll just put it above the scene, kind of like where the camera is. So this is the light position. And then the light vector, the light vector is going to be a vector that we draw from the surface position to the light position. So vec3 light normal equals normalize, and we're going to go towards the light. So this light position minus the point on path, which is the surface collision position. So I think of it as point on path, and I think of this as an arrow going right to left to the light position. So that is going to get us a normal pointing towards the light. And this is our surface normal, which is perpendicular to the surface. And then by taking the dot product, vec3 light intensity equals the dot of the light normal and the surface normal. And because dot product is just analyzing the angles between two vectors, we don't care about what the order here is, because the angle between two vectors isn't going to change if you swap them, right? Like if you take a peace sign, right, and you flip your hand around, it's still a peace sign. The angles between your fingers is still the same, right? So for the light intensity, that is a float, and we could say light intensity here. And then we can just take the hit value, which is 1 when we've hit geometry, and just multiply it by the light intensity, and we should get something that we can work with. So let's take that and just see if we have enough feedback to where we can confirm that we actually do have a sphere. So that looks like enough for me. I'm convinced. So the next thing we might want to do is we might want to just move the light a little bit. So let's just say instead of minus 0.1, let's just do the cos of I time, like that. And if we do that, we should have just an animated light source that's kind of like going back and forth. It is going back and forth, but oh, that is very, very subtle. So we're going to multiply it by 3.0. And we also might need I time to go a little bit faster as well. But you know what, let's start off with just this and see if that gets us something that we can observe. Yeah, so I think I want that to go a little bit faster, so we're going to multiply that by 20. And if we take that... Oh boy, so that kind of makes it look like it's moving. I mean, it's there. Let's increase this distance here. So let's say, let's just use 10, just so you can get an idea of like where this light is. Okay, so let's take that and so I would say you know what it is? We also should probably put the light kind of like up a little further, maybe. And let's use 100, I guess. I'm not really sure what the scale is of what this canvas I'm looking at. The scale kind of seems a little weird to me. Let's slow down eye time. I think it's going too fast now. Okay, you know, like, you know, not the best, but it's something we can work with, right? Okay, so now that we have this light intensity, and let's work with this, what we're returning here. So let's add like a global illumination. So, so we'll do like float GI equals like 0.01 or something. I don't know. Oh, no, let's just do something a little bit high until we figure this out. Global illumination, and then for this light intensity, we're just going to add 0, 1 like that, right? Sorry, not like that. We're gonna actually use the variable we defined. It's a little bit of global illumination, so the in the shade part doesn't go completely black. And we might want to pump that up a little bit. Maybe 0.3. And, see, I have some problems with my ray marching where, I think I need to... I'm not exactly sure why I have some artifacts in this algorithm. But it does appear that I do have, like, an artifact on this. Oh, you know what? No, I don't. My screen is just dirty. Okay. Let's pump this global illumination up to, like, something ridiculous, like 1.0. And the reason I'm doing that is because I really just want to confirm that that global illumination is actually being applied. Okay, yes, so it is actually being applied. So let's use 0.4. 0.5 is, you know, that's a little extreme, but I really just want to be able to see what's going on here. So let's remove this global illumination from here, and let's just, like, give, like, a dark red global illumination. Like, let's say li.x, so the red equals gi, li.y equals, we actually don't want a equals, we want a plus equals. X, Y, and Z. So this is, actually, this is vec3. We're going to call it LT for light tuple. Light tuple. And then LT dot X equals right, we'll take that, this light tuple, and we'll just give it like a red global illumination, and then we can just take this, and we can still multiply it by a scalar. And if we want to be explicit, we can do XYZ like that, and I think that it'll multiply this, give us a XYZ, and then actually, I don't know if that'll work. Hold on. Let's just do, I don't think that's gonna work. I don't think it'll be able to derive that. I don't think it's gonna automatically extend that last value. So what we're gonna do is we're just gonna do a vec3, and then we're gonna do like a vec4, and the vec4 is just gonna be the hit value. So some of the we lost some of the succinctness we had earlier. But yeah, so let's give that a shot and see what we got. X field requires structure, vector, or blah blah blah. Okay. Really? So that's interesting. That makes no sense to me. Um, you know what? I think that maybe, this is a, okay, so this, I think what this might be is that when we declare the variable, it may have not. No, it should have reserved the memory because this is not, there's no pointers in GLSL, so it's not like this is a null pointer or anything. It should be like a data, create the data structure. Um, but we want to make sure we can do like a vec3 0 like that, and just make sure, because you know maybe I was wrong, you know. Field selection requires structure, vector, or interface block on left-hand side. So I have no clue why that is wrong. So I'm gonna go check that bug out or the mistake. Um, am I doing something really stupid? It's just not. Yeah, I don't understand why that is. Okay, so what we're gonna do is I don't know why. So I don't know why I can't do this. Okay. Okay, so I don't know why that is being like giving me a big fuck you. So we're just gonna take that and we're gonna paste it. And then we're just gonna we're just gonna take we're gonna take LT right, so I'm pretty sure it was the left-hand side that was causing the problem, so same deal. Now we could be a little bit more concise about this, but I just want to see if that actually works. Like, I want to make sure that that this syntax is allowed, and I want to kind of isolate. X field selection requires structure, vector, or interface block on left-hand side. So I think it, do I have like a LT somewhere else? No, it doesn't look like I do. So it doesn't like this either. I have no clue why that is a thing that it's like, oh wait, light intensity. Yeah, that would be a thing. So I see what I did now, because I think I'm tired. So light intensity, we're kind of just expanding this light intensity, which is the float. So, okay, so if we take that, and we're expecting kind of like this red global illumination now. So it almost makes the light look kind of red. So let's just tone that global illumination down a little bit. Okay, so there's much to be left. left to be desired here, but let's just say, you know, that's good there. So let's say done is the orthographic camera, done is the ray march setup, and done are the lighting calculations. And now we need some type of hard-coded tile map structure. So let us take what we currently have, and we're gonna just paste it into. We're gonna edit the SDF post. I'm gonna edit the paste bin, so that way up here. This paste bin, these paste bin URLs and whatnot, and the tiny URL, tinyurl.com/sdf-005. If you want to go look at the source code, I am updating it right now. So save changes. Okay. And just looking through it, making sure that the changes are actually there. We just did SDF, the new stuff is in SDF render, so if we look at SDF render, I have my lighting color. Okay, so I was just verifying that those changes are there, so you can go to tinyurl/sdf-005 and you can check that out. Okay, so now let's get to doing some type of tile map. So the way we're going to do that is we're going to have some type of tile map data. So we're going to have a int tile array, and it's like I don't know, it's let's say it's like I don't know, 100 on the X, and let's do 64 on the X and 32 on the Y. Let's say we have something like that. Actually, equals, and then I believe for a hard-coded constructor for array, we need to do like these kind of bubble brackets rather than if this was C code, we would use a constructor like this. But to initialize this, I believe we're gonna need these kind of brackets. So now I can look at some other code to verify that. So we could do that. So I'm gonna do I'm just gonna open up a folder with that has some default shader code in it. I'm just gonna take a look at that and see if so I know that these default shaders here will have no, that one will not, but the other ones. So I'm using a uint 8 unsigned char. Oh, I see. Yeah, the constructor is a little bit different. You know what? Let's just take this. That's some good stuff. Yeah, that's exactly what we need. So let's just take that. Let's just roll with that. Let's just paste that in there, right? And unsigned integer 8 bits. Our blank spots are spots that have something in it, and we've kind of like written some stuff. The tile map is 25 on one axis and then 7 on the other axis. So yeah, that looks good to me. Let's kind of like align that up. Okay, yeah. So hopefully you can kind of see what is going on here. And it's not really a message array, it's more like a tile map now. So, I don't know what we're gonna call it. But But we could call it tile array, or we could just call it array because we don't have any other arrays. Let's not do that. Let's call it tile array. Okay, so with that, we save that. Let's just make sure that that is acceptable in ShaderToy as it is, because different versions of GLSL can be slightly different, and it might not like that. Illegal use of reserved word. Really? What did I use as a reserved word? Unsigned. Really? Unsigned care. I think that might just, So, you know, I really don't care, if it's signed or not. This'll matter in the future for some stuff I'm working on. But let's just use it int for now. But I really would like to be kind of explicit, so the UO8 is going to be changed to I32 for int32. So we have integer tile values instead of unsigned characters, or unsigned bytes, whatever you want to call them. Let's take that, and let's see if that is working, and we still have some type of mistake here. We see a syntax error. I'm going to guess it does not like my extra semicolon. It's being really authoritarian with things that don't really matter. Yeah, I didn't like the extra semicolon. So usually when I write code, I just put an extra semicolon when the statement kind of exceeds one line. So if I see, usually if I see a semicolon and there's two of them, I know that it's a multi-line statement, and if I don't see two semicolons, then I know it's a one-line statement. So like this right here, I know it's a one-line statement because there's only one semicolon. But it looks like at file scope, we're not really allowed to just add semicolons willy-nilly. Okay, so that is just a little tile map. So now we need some way to like render this. And in order to render this, we obviously need the tile array, and we need to figure out which tile we're kind of like intersecting with. So for that, I am going to... So I already said these spheres were like 1 by 1. So we have this SDF render. This is SDF scene. And because we're doing SDF scene like this, and we are going to do some grid collision, now we actually do need the we actually do need the origin and the ray, because we're going to use kind of like some space partitioning to... We're not... Like, if we have hundreds and hundreds of SDF things, I don't want to do like a min on like all those. They would be so inefficient. So since we're looking down on it orthographically, we can see which cell we're looking at on the tile map, and then render a SDF sphere within the center of that cell. So let's do that. So we do already have a we already have the hard-coded tile map. So where we're really at right now is this is really where we're at. We're at tile map rendering now. So let's take SDF scene, and we're gonna give it the origin and the ray, and then the point on path. And then we're going to go up to SDF scene, and we're going to do vec3, the origin, vec3 org, vec3 array, and origin array, and the point, right? And obviously we didn't actually change anything, but we're going to need those extra parameters if we're going to implement this grid. So giving that a shot, we already screwed something up, and it's like, how did I screw something up when I just, like, you know, I thought you know what it is? I'm calling SDF scene in more than one place, aren't I? Mm-hmm. Yes, I am. So we gotta take the signature here. And with snorm, org, array, and point, we need to do that as well. So org, array, and then the point on path. And from here, we're just gonna say that org and array are in the beginning. So we'll do org and array. And that's getting a little bit verbose for me, so I'm just going to do like OR, like that. And I'm going to just add 2 more defines. So instead of sexy Z, it's sexy Zor. What does that mean? I don't know, but I can remember it, because it kind of reads like something, right? Okay, so with that, O and R, and O and R are going to be the origin value and the array value. Origin and the array. Okay, so we mildly refactored that. Okay, so that works again. So now we're gonna implement some grid collision here. So this SDF sphere, we want to change so we're going to have the org geometry. And then in an SDF sphere, we're going to do vec3 org geometry like that. And then for this, we're going to do vec3 org geometry equals vec3. And we're just going to put it at 0, 0, 0 again. And we're just doing some refactoring where we take this, and so the 0, 0, 0 is no longer hard-coded, but the radius is. And we're just expecting, we're not expecting any changes, we're just expecting that the code still runs. Okay, so the code still runs. So now what we're going to do is So this is only going to work for orthographic camera, but I'm going to try to calculate where the ray is intersecting the tile map. So we're going to say that we're going to say float px, for like pixel x, is equals ray.x. Actually, no, because the ray is going straight down, right? Well, actually, no, because the ray, right now the ray and the origin are kind of like very similar. Yeah, so it doesn't really matter. We can use ray or the origin. Yeah, it doesn't matter. Only works for orthographic camera. Naive. Okay, so this is a naive calculation. So we're gonna abstract things as pixel x and pixel y. And then from the pixel coordinates, we're gonna try to calculate a tile coordinate, right? So the index of our tile, and you know what? We also have that in our shader. So let's look at that. So yeah, let's just take all this and paste it here. So GFC, this GFC right here, that is going to be our PX and PY. So it's PX, pixel X, pixel Y. Okay. And I will go over this really quick about like what is actually going on here. So the number of tiles X, number of tiles Y. We need the size of our tile map. And using the size of the tile map, we can get the width and height of a single tile by dividing by the number of tiles on the X and Y. The tile X coordinate, the tile Y coordinate, we just see how many. If you take px and try to chop it up into units that are the length of a single tile, how many tiles worth of data do you get, right? And that's going to give us the index of what tile we're in on the x-axis, right? And if we have less than 1, like if this ends up being less than 1, like it's 0.5, that's going to floor to 0, and we're in the 0th tile. So the tile indices start at 0. So this is the same thing, but for the y-axis. The index of the tile, number of tiles on the x multiplied by the y tile position 2D, and then we just add whatever remainder is left over for the x, and that'll give us the one-dimensional position of the tile. And then we can get the tile value by just going into that array, which we call tile array. Yeah, and the other thing is that we are now using int, so we kind of refactored that a bit. And that also means that with this comparison, that we got to do that. And now, the other thing is, you know, this is two cases here. So if we are not hitting a tile, like the tile value is 0, then what we want to do over here is return max distance plus, I don't know, so this is just gonna say we haven't hit anything. I'm just giving it a decent amount of padding here, so I'm just making sure that it's absolutely out of bounds. Let's just say we're out of bounds. We're not going to hit any geometry at all. No geometry in this cell. So there's just no geometry in this cell. That's what we mean there. And then otherwise, we're going to do SDF sphere in the orange geometry in the point position here. And to do that, we need to change orange geometry dot x equals tile x times so the width in pixels of each tile. And then we really want the center of each tile. So if we're on tile 0, if this is tile 0 here, if this is tile 0, when we multiply we get 0. We want to get to the center of the tile, so we want to add TPW divided by 2. That's going to give us the... So this is going to say that, you know, if there is a tile that exists, we just want to render this SDF sphere where that tile is, if that makes sense. So orange geometry.y is tile y. The height divided by the height. And the other thing is with the orange geometry, XYZ. So we're still going to say that this tile map is like on the ground plane, because I think it's just going to make things simpler. And do we have to say float? I don't know, but now we are. So we're going to say float. Line things up nicely. Okay. So now the origin of the geometry is going to be at the center of this tile, center of this tile. Now, do I have my units correct? I don't know. We could have some really weird intersections. I'm expecting like a barrage of geometry. But we're going to get something interesting, that's for sure. So let's take that and run with it and see what happens. And syntax errors abound. Okay. So let's take float. So the first thought here is Well, once I get the syntax errors out, I don't expect this to work perfectly. I'm not sure exactly what I'm going to see, but I assume whatever I see, I'm going to be able to fix. Mm-hmm. Oh, okay. Okay, so that is running, and I gotta say, it's not looking good. It's completely black. So to simplify this, let's say that if we do have a hit, we're just gonna return 0, just to like get some indication of if the cell, if we collided with the cell or not, right? And we'll figure out the other math once we get that working. And so right now it looks like, for whatever reason, okay, so we have to figure out why SDF scene is basically, it's always black now. So that's great. So let's do a little sanity check, where we're gonna just comment this out really quick. Oh, yeah, that would create a problem. Okay, so let's see what I did with my sanity check. But we might as well carry it through with the sanity check. So where I'm using SDF sphere again, no, I mean that's correct. Okay, let's slowly build it up here. So let's say that this orange geo, we're gonna just return orange geo, and then we're just gonna comment this part out, right? So let's take that like that and see what we get. And we got nothing. So I know this is the no geometry condition. But let's just call the same thing and both. So this orange geometry is already set up here. So what I'm expecting is I'm expecting to still see the same result. Okay. So my first thought is that when I'm moving this grid, these units are much more extreme than I think they are. So if I add a 1 there for the geometry origin, we want to see like how much does that actually shift over by. Because it might actually be shifting over by quite a bit. And it's a pretty big shift. So what we're going to do is we're going to say just going to try to scale these tiles really quick. We're not going to worry too much about is that correct, is that not correct, what's the exact math. We just want to get something on screen. So So, you know, we'll just make, like, float versions of everything. So, float... So float tile X, float tile Y. And then these are float versions of these. And then we'll just put the S's for scaled. Actually, no, let's be more consistent. Let's just use F. I know we're applying a scale, but let's just... For some consistency, let's just put F's. And then we'll put F's in front of this. And now we kind of have some scaled stuff here, right? Yeah. Okay, so let's take that. And see if we made any mistakes syntactically. Yes, we did. So now that those are float again, we gotta divide by 2.0. Okay. So we've got it rendering. And I think that it's always saying that it's not in the cell. And why would that be? Yeah, I don't know why that is, but it's definitely only executing the so if we go over here in the no geometry thing and we just return like a 0.0, I'm expecting that the whole thing kind of like lights up whitish or something maybe. Or just nothing at all. But yeah, so I know that that this SDF sphere, this first one, is the one that's kind of being called. The other problem I'm seeing is that it's moving. Why is it moving? Is it moving? Oh no, it's not moving. It's that light. The light is very extreme, so it appears to be moving, but it's not moving, is it? It's just that light is kind of crazy. Yeah. So for whatever reason, something about this math is not quite correct, and we're never getting into this tile value thing. So we see x is 1, so we do have an array of integers where we do have something that is greater than 0. And for whatever reason, we're not seeing anything rendering. And so we're either not getting in here or... well, let's... so I guess we still can't assume that we're not in here. So let's try... Let's just try that. Quick and dirty. Because maybe we are getting in here, but there's no, like, correct translation or something. So I would say... No. It's not about that. It's that... This is the only one that's executing. Yeah, so if we take that, and we paste that in there. So it's definitely something about our collision with the grid is not quite correct. So we have to think about how we're doing that. Okay, so one thought is... there is the chance that we're going to end up out of bounds, where tile X and tile Y are like greater than the number of tiles. Alternatively, they could be negative. So we should probably protect against those cases. And so if tile is greater than or equal to 25, or tile Y is less than 0, or tile Y is greater than or equal to 7. If these conditions happen, then we are not in there. Out of bounds. Okay, else. So otherwise, we're going to take all this, and now we'll calculate the tile value using the index of the tile. We can also put that in here. And so let's give that a shot. So I'm expecting that maybe we'll see the out of bounds condition. And yeah, let's just try that and see kind of what happens. Let's make sure it still works. Okay, so still running. So what I'm wondering is if I comment this one out, if the out of bounds condition also renders, and I can still see a sphere in that position. And the answer is no. So it's not out of bounds. So I'm assuming that it's not out of bounds. It's in bounds, right? Like, so we know we're in bounds. Like if we just put this one here like that, and we run it, we're gonna see, oh yeah, we're totally in bounds, where I'm kind of expecting that to be. So we're definitely getting in bounds. So if we're out of bounds, we're going to do this. And then if there's no geometry in cell, we're also going to do that. And we're going to take this, we're going to run it. I'm expecting not to see anything because we still have some problems. And we're still seeing something because we have this SDF sphere here where we're just debugging. If we take that, comment it out, now we should see nothing. Okay, so with that, now we got to look at this code here and be like, okay, there's a few possibilities. One is that that we're always getting no geometry in cell. So let's to figure out if we're actually getting into here, we can just go like this, Control A, Control copy, and see what we get. So we're never getting a tile value. We're just not getting, like if we put it over here. So we're somehow in bounds, but we're not able to derive a tile value, which is like, or you know what, we could be, we're not certain of the scale of this right now. So what we should do is like, we actually just might be zoomed in on a section to where, like, it's rendering, well, obviously it's doing whatever we told it to do, right? The computer's doing whatever we wrote. But there's a possibility that maybe it is, it's zoomed in by some factor, and we're just, the entire, there's like one cell filling the entire area, or one chunk of empty cells filling the entire render area, and that is why we're always getting an empty cell report back. So let's take this and let's just make it all X's. So now none of the cells should be empty now. So we take that, and now we take that to the bank and run it. We got a problem. What is our problem? So we have a syntax error because this bullshit, right? Yeah. So the very end right here, we got to make sure that we included our commas. Okay. So now now we have this grid. So now it's like anywhere on this grid should be a collision because these x's are defined to be 1. So let's go back over here where we have this cluster of horribleness. And let's just get rid of this node geometry in cell 1. And we're only going to keep this SDF sphere. Yeah, and the goal is to actually just see at least one sphere. Okay, so we still have at least one sphere, so that's good. So now what we're gonna do is we're gonna put back this these calculations and see if we can get like more than one sphere kind of showing up, or see what we can kind of get here. Okay, so we have a single sphere, and I would say that we gotta figure out what's with the scale factors here. So I'm gonna make it like the scale factor like 1.0 first, to see maybe things need to be closer together. I don't know. Well, that wasn't it. So dividing it by 30. Let's divide by, I don't know, 60. How about 70? 80, whatever. So I am kind of lost here. So we could try something less extreme. So one thought is, let's just normalize. Yeah, I mean, that looks correct. So I'm not sure why it's like always uh, rendering in the center there. Um, yeah, well, you know, one thing we could do is we know that this part is actually rendering now. So let's save that like that. Make sure that when we comment it out, it no longer shows. Okay, so now that we know that no longer shows, let's try to figure out which tile that it is rendering right there, right? So let's go over here, and if we make this one like blank, right? So, you know, the most obvious one, right? Or the one I think is most obvious. So let's run it now. Okay, so not showing up anymore. But if we put an X here, save that, A, Control, and then we go Control A, Control V. Okay, so it's definitely this corner is getting rendered, right? So I think that probably something with my Tilemap math is just being like I think we're getting some weird kind of like truncation where this value is probably like always it's always this value is always 0 for some reason. So we gotta think about like why would it always be 0, right? Um and so we know that our uv.x and uv.y are kind of like centered in the screen currently, which could be creating oh, that's definitely creating some problems with this, right? Because then we're trying to do all this math with this px and py, but px and py end up going negative, and none of this math should ever be using like a negative pixel coordinate. So we want to like undo. We definitely want to undo whatever we did. That's what I get for centering the coordinates. So this coordinate centering stuff here, we can't have this, because it's nice usually in a shader, but for our purposes, having the UVs and the origin like this are just making things difficult on us. I absolutely know this is part of the problem. So vec2 UV, and now as far as oh god, yeah, it's even worse than I thought. It's so the UVs are also like a scale down 0 to 1. So okay, yeah, so we definitely it's definitely has to do with this. So let's hold on. So I have some solutions in mind now. So when we look at where we're colliding with this tile array, we know that this px and py right now, if they're the orig x, orig y, those are like normalized coordinates from not sure what the coordinates are, but they're normalized in a range of like negative something close to 1, and then positive something close to 1. They're in kind of like that 0 to 1 kind of range, because we divided by I resolution. I'm not sure of the exact range because we have a rectangular canvas here. So with that, we know that these are float values here, and we can't be doing that. So to fix some of this, we can try to undivide by whatever we scaled it down by. So if we look at this, we divided by resolution.yy. So since we divided by resolution.yy, we can undo that by multiplying. Now, it's not going to fix everything because we're still going to have the origin of the tile map. We're going to have the tile maps 0, 0 still kind of like in the center of the screen, which isn't what we want. But I think that we'll start to be able to get some feedback and get some we'll be able to get some feedback where we'll start to be able to see some things, right? And it's not everything that's going to be correct, but it's going to get closer to what we need. So, because these are pixel coordinates, right? So we want the frag coords. We don't want the UVs. So if we take that and we paste it, I'm hoping we're going to get like a big cluster of stuff starting from the origin and going right and down maybe, or in some direction, but I hope to see multiple spheres now. Okay, so, oh, excellent. So we're actually getting somewhere now. So we got like this tile map kind of thing. Now to fix this, we could just translate everything. We could translate this tile map by whatever let's undo more of these operations, right? So if we're looking at these operations, right, we undid this one by multiplying. And then we took the frag chord and we minused 0.5 times iResolution.xy. And those are the respective pieces. So we're going to add both of those to undo that, right? Yeah, so we're just going to add, we're going to invert that, we're going to add it. So right here, well, not right here. Px plus equals must okay, so we're just undoing the transforms so that we can turn these back into fragment coordinates. So now let's take that and play that. And that's not what I expected. It's let's do a minus equals, because I'm gonna guess that we just translated in the wrong direction because I can't math, I guess. And no dice, huh? Okay, so let's take another look at this because obviously I can't do algebra. So if we want to get the okay, so it's UV times the iResolution dot so this is times, right? Yeah, we times and then so then we times by that. Then we have this left over, and so we want to get back to the frag chord. So in order to get back to the frag chord, we want to add I feel like we should just be able to add 0.5 times I resolution dot x and I. Yeah, we need to add. But I'm not sure why that's not working. So it needs to be a plus equal. Yeah, I don't know why that isn't working. So, well, hold on. Let's just keep 0.5. I don't know. Let's just throw something in there that's not too extreme of a value and kind of observe what happens. Well, it kind of makes sense that it would be intuitively. I think this would be what would make sense. So I think my algebra just sucks. So let's look at that, see what we got. We got nothing? Really? Oh yeah, because it's wrong side. Oh, you know what? Okay, let's try plus equals. Okay, so what the hell? What the hell? Let's try like 20, right? So if we just offset it by 20, what do we get? Is this not what I Okay, so that's kind of like what I am expecting. Where so oh, you know what? Yeah, so having these different coordinate spaces is definitely creating some trouble for us. Where we are, where we're just in trouble with, yeah, having these different coordinate spaces is just asking for trouble. So 100 isn't working. How about 50? We don't want to just get it, like, off the... Okay, so 50. So when we add, we do want a minus equal, because that's going to back it into the screen. Okay, yeah, so it does... It's like, yeah, so having these two different coordinate spaces is just bad, bad times. Bad times. So in order to get this working, I think what we need to do... There's a lot of ways we could, like, get this to work. What I think would be easiest is what I think would be easiest, because this is just gonna be a pain. So I'm definitely seeing the problem here. Besides the spheres, you know, so we could. So these tiles need to be. How are we offsetting the tiles? Are we, So the tile pixel width, we can actually use the actual width of these tiles, I think. So we're just trying to... float. So now I'm just gonna try to, like, So there's some things that are botched from when I was troubleshooting, and other things are just botched for other reasons. So the pixel width, I resolution, .x, divided by float, number of tiles. So that seems like a reasonable way to do the width and height of the tiles. But it's not, like, there's some weird transforms going on here. Yeah, because then when we go back into here, we have to, yeah, so this is just a pain. So I see what's going on here. It's, that when we go back into this geometry stuff, we want to go, like, we got the pixel, and now we need to go back to the UV again, right? So this is just annoying as hell. So these are, like, so these are actually the, so let's, move some of this. So we just have to transform between our different coordinate spaces. So we're going to do tx, ty, tz for the tile x, and tile y and tile z positions. And, float tx, tile x position in 3D frag coords. So basically, right now the x, y, and z, they're like three-dimensional frag coordinates. And for this geometry, we need to, once we figure out what tile we're in, we got to take whatever transformation we did to get these pixel x, pixel y, and we got to untransform that. So now we're going to take the pixel x, and we're going to divide by iResolution.y to get it back into the coordinate space that we need to be in. As far as Z goes, I don't really know. I mean, TZ is at 0 anyways, so it's like, you know, I don't know, we'll just say times 1 for now. But yeah, so I'm pretty sure that what we need to do here is just, we have a coordinate space problem on our hands. So let's just kind of keep on doing that. PZ, undefined identifier, right? Because this is still, oh, and these are T's. Oh boy, that would have been bad. We would have never figured it out. Okay, so take that. And see what we screwed up. And this needs to be a 1.0. Okay, so we have we got something, like we can see that right on the edge. It's definitely not exactly what we need. So I'm not sure. I'm really not sure what's going on here. I've made some type of mistake somewhere. Um, the coordinates are. So I need a better. We kind of like wung it. I was like, yeah, just first we render a sphere, and then we just try to remap rendering the sphere, based on like this grid, but the tile map grid is using pixels, and then the other coordinate spaces is using like normalized coordinates. Having those two different coordinate spaces is really screwing with us. So we need to really think about what are our coordinate spaces and like how we're gonna do this math. So I think it would make more sense to so the fragment coordinates are already on the screen. I think it would be easiest for us to just try this again tomorrow. But then what we're going to do is we are going to we're going to keep a more uniform coordinate space, because I kind of understand what's going wrong here, but it's like even if we fix it and fix all these transforms so that everything is correct, hold on, let's move our light before we. So yeah, let's move that light a bit, because there's probably more over well, yeah, let's move that light, and yeah, because we might, yeah, let's move the light. But yes, having these different coordinate spaces, I think we should do everything in the coordinate space of the fragment coords. And yeah, I think that would make it easier. We shouldn't be messing with two coordinate spaces. That's asking for trouble. I can see why you would do it in some cases, because it can make some types of math easier and it can simplify things. But in this case, I'm not sure if it does. So let's see. So we have the scene, and we have the estimation of the normals. We have the rendering, and our light intensity, and then our light position right here. So I don't think it's really well, let's just crank that up to 200. I'm just gonna crank it up to 200 and see if we end up, because we see that little hint of another sphere. And the question is there like more over there that we're just not seeing because the light isn't moving far enough? And I think the answer is no. The answer is yeah. So we've kind of figured out what's going wrong here, but it's well, actually, eye resolution. Oh, well, yeah, that's a problem. The origin X, eye resolution Y, and we want oh, I know why we did it that way, because the Yeah, it doesn't really matter. It doesn't matter if, that's not going to change it enough to where we would actually... Yeah, okay, so I get why what we're doing wrong here. So let's just take this. Let's just try to get something where we can kind of see some type of thing. So we're not, like, ending on a note where we have nothing to work with. And it was this, and then with px and py, we'll just do times 1.0. So yeah, we have a problem with our coordinate spaces. That's absolutely what's going on here. I don't even know what the hell. Right, and this was like, we made this like 1.0 or something. So, okay, so this is just, we're gonna do our handy dandy Control Z because we've messed around. We kind of have a clue as what the solution is, but even if we fix the solution, we still have the weirdness of these ununiform coordinate spaces, and so it's not like, it's just a bad design as far as I'm concerned, because fixing it feels kind of hacky, and more, you have to like add this extra code to transform between these coordinate spaces. We don't really want to think in two different coordinate spaces, so what we're gonna do is we're just gonna keep on going until, let's try to save that, and let's just keep on running it until, we're just gonna keep on Control Zing until we can get back to a point where we got like the kind of array of stuff. And if we can't, then oh well, because okay, let's try that. Okay, so now we have that little array of stuff, and you know, I think that we're actually onto something here. So let's try to so like if we take these spheres that we're rendering and make the radius like a 0.5 or something smaller, let's try to fix what we can fix. Okay, so yeah, I see a problem here where like this first one is kind of where it needs to be, and then the coordinate spaces aren't quite lining up. So this definitely has to do with having these two different coordinate spaces. So if we take this, I'm sure that this image is also inverted as well, because this is our, I guarantee is our, so if we make this over here, if we do that, this one right here is going to disappear. I'm fairly certain. Let's give that a shot, see what happens. I could be wrong. Yep, that one disappeared, right? So we have kind of like this crappy tile system, but we botched it, okay? So the problem here is definitely our coordinate spaces. We tried to define a tile map where we're like, yeah, let's just wing it, and we're going to define the tiles in number of pixels, so we're going to use fragment coordinates, but all of our rendering is not using fragment coordinates. It's using these transformed fragment coordinates that are then squashed into UV coordinates. And so now we have this problem where some of our math thinks that, you know, the world space is all about these normalized coordinates, and then another thing thinks it's like about these like pixel coordinates, and getting those to line up. You know, if we were really careful and we knew exactly what we were doing, we could keep it where it's like we use UVs for the ray marching math, and then we use the pixels for the grid collision. But that's just so much extra work, so much extra thought, extra code for converting between those coordinate spaces. We really want a uniform coordinate space. So I think what we need to do is tomorrow we're going to rewrite this, but when we do our ray marching engine, we're going to do it in terms of fragment coordinates. We're going to get our fragment coordinates so that the fragment coordinates are in terms of like graphics origin. So we're gonna flip around. We are gonna mess with our frag chord a little bit so that our pixel coordinate starts at 0, 0. It starts at the upper hand corner here, rather than the GL origin is usually down here. That's why you're seeing things kind of flipped around. So we'll do some transformation of that coordinate so that it's up here and lines up with the graphical origin. But then we'll do all of our math in terms of pixel sizes, right? So we'll use some type of size for a tile that kind of makes sense, like 64 by 64 pixels, and then we'll just map it directly to the screen, right? Right, because we have this tile size. Yeah, so there's a lot of stuff we need to do. So I'm gonna just update that we failed. So I am going to take the code that we have. I'm gonna put that into pastebin. So all this code right here, you can go to tinyurl.com/SDF-005. You can go there and take a look at this, but this is completely botched. It's not worth recovering, because trying to recover this code, it just has a fatal design flaw, you know? So it's not worth trying to fix. It's better just to start over. So we're going to burn it in a fire, and then we're going to start over. So, you know, if you want this for reference, to see what it is, because maybe you think that you can fix this the way it is, because maybe you see what I've done, and you're like, oh man, you're so close, you know? Because maybe you're smarter than me, like I'm not a complete genius, you know. And if you see what's going on and you want to fix this, be my guest, have fun. It's also good for reference because I can kind of see what I've done wrong. Okay, so I saved those changes. I'm gonna absolutely make sure that this URL works. So let's take a moment to full screen this. And so I'm going to full screen this. I'm just going to open up a new tab, close this tab. I'm going to go paste that tiny URL /SDF-005, hit enter, and just see what happens here. Okay, so it goes there. And if I take this code, I'm going to look at the raw. So there's raw paste data. If I go Control A, copy it, then I'm going to just go over to my shader toy really quick, and I'm going to see if that works. So let's go back to shader toy, and I'm just going to paste it into here, and then I'm going to hit enter. Oh, well, not enter. Well, yeah, I can hit enter. Then we're just going to go back here and make sure that it's still working, and yeah, it's still running as expected, in all its horrible glory. So now we know what needs to be done next. We know what the design mistakes from this kind of proof of concept idea was, and we can try to tackle it again tomorrow. So this is about a 3-hour stream. I'm going to end the stream here, and yeah, later.